Hello everyone, I'm İlke, and today I'd like to talk about my Physics 101 project whose name is Conservation of Energy in Horizontal Atlas Machine. Basically, my objective in conducting this experiment was to show that the mechanical energy of a system would be conserved if there are no non-conservative forces acting on it, and also expressing the relationship between kinetic energy and mass. For the theoretical background, I used energy formulas for the translation of kinetic energy, potential energy, conservation of mechanical energy, Atwood's machine, Newton's second law of motion, and motion formulas for displacement and velocity. For the setup, I use an airtable, string block, pulley, electronic scale, black carbon paper, white recording paper, puck, and rulers. First off, I started by measuring the masses of the objects, then I attached the string to the puck and the block, passed the string over the pulley, moved the puck to the opposite side of the pulley, measured the height of the block, and let the puck slide so that I could measure the data. So here's an example of me doing the experiment. After I conducted the experiment, I transferred the data to my data tables, and the first data table I have is the variation of displacement and height as a function of time. Using this data, I plotted a graph of displacement versus square of time, and I used the slope to find the experimental acceleration value. And I also calculated that I had an error of 13.7%. Another data table for the masses of the objects, another data table for the variation of velocity, kinetic, and potential energy as a function of time. I calculated the corresponding velocity values using the accelerations, and the kinetic energy values using the corresponding velocity values, potential energies using the corresponding heights, and also masses. Another data table for the variation of total kinetic energy and potential energy as a function of time, where I included the total kinetic energy of the system and the potential energy change of the block and the corresponding errors. The errors indicated that the potential energy change was not fully transferred to the total kinetic energy. Here from the graph I plotted, I can see that the total kinetic energy, which is the sum of the kinetic energies of the objects, is almost equal to the potential energy change of the block. And also, there's a certain proportionality between the kinetic energies of the objects because they move at the same velocity, but they have different masses. Lastly, a data table for the variation of mechanical energies as a function of time, where I included the individual mechanical energies of the objects and total mechanical energy of the system. From the conservation of mechanical energy graph, we can see that the individual mechanical energies of these objects changed, and the total mechanical energy of the system remained almost constant. The mechanical energy of the block decreased because the change in potential energy of the block was distributed between two objects so that they could have kinetic energies. At the top, we can see from the mechanical energy versus time graph that the mechanical energy values fluctuated a little bit. That's why I got an error of 0.169%. As I said, I had some errors, and possibly the reason why I got errors in acceleration was measurement mistakes I made and ignoring the mass of the string and friction. Potential energy wasn't fully converted to kinetic energy. That's why mechanical energy was not fully conserved, and these are probably due to the loss of energy due to friction, and also some of the energy might have been converted to rotational kinetic energy of the pulley. Overall, mechanical energy was almost conserved, and potential energy was converted to kinetic energy, and the kinetic energy values of the puck was nearly 13.5 times of the blocks because its mass was also like that.